Imagine Earth some 15 or 20 million years ago. The map of the continents already looks quite similar to today's, but the climate is not. The planet is warmer, the poles have less ice, sea levels are higher. Large coastal areas that are now above water were then covered by shallow, warm waters teeming with life. This is no small detail. It's the perfect kind of ocean for a superpredator to emerge. In that world, the sea was a seething laboratory. Whales were in the midst of an evolutionary explosion. Enormous forms filtered plankton. Smaller ones hunted fish. The first lineages were also emerging that, in time, would give rise to modern toothed whales, capable of coordinating complex hunts. Around them swam schools of bony fish, giant squid, sea turtles, primitive seals, and other sharks of respectable size. The food chain had many rungs. At the top, all indications point to it. Today we call it the Megalodon, the Great Tooth. He was a gigantic shark, probably the largest fish predator that ever existed. He didn't live in an isolated corner of the planet. His teeth appear in sediments on almost every continent. Remains have been found in Europe, on both coasts of the Americas, in Africa, in Asia, and in Oceania. That tells us something very simple and very powerful. It wasn't a local anomaly. It dominated much of the world's temperate and tropical seas. Its history spans millions of years. Fossils place it between the early Miocene and the Pliocene, roughly 23 to 3.6 million years ago. This means that this shark coexisted with several generations of whales and marine mammals that changed with the climate and currents. While cetacean species appeared and disappeared, it remained. It adapted, followed prey, and took advantage of warm ocean corridors. For a long time, it was one of the constants of the sea. When we talk about its size, we enter slippery territory. We don't have the complete body. We don't have articulated skulls or fossilized tails. What we do have are colossal teeth, up to 16 or 18 centimeters tall, and some enormous vertebrae. With this data, various studies have estimated lengths of at least 15 meters. Other, more recent models push the limit to 18, 20, or even more. In any case, we're talking about an animal several times larger than a modern great white shark. To put that in perspective, a great white shark is around 5 or 6 meters long. An average specimen of this prehistoric predator would have been 2 or 3 times that size. Some exceptional individuals, according to certain models, could have rivaled the length of an articulated bus. And it wasn't just long. Body mass estimates suggest tens of tons in adult specimens. A body like that requires a lot of energy. To sustain it, the ocean must have been incredibly productive. That's why the climate context is so important. In the Middle Miocene, large areas of the ocean were veritable all-you-can-eat buffets of nutrients. Intense upwelling, warm currents, and wide continental shelves created ideal conditions for plankton. Plankton fed small fish fed medium-sized fish. And at the top of the food chain, large whales and marine mammals became the ideal prey for a predator that needed to eat a lot, often. Another key factor is temperature. All indications are that this shark preferred temperate and warm waters. Most of the fossil finds are concentrated in ancient marine basins that, in their time, had higher temperatures than they do today. This doesn't mean it couldn't venture into somewhat cooler areas, but its thermal comfort zone was linked to warmer seas. When those seas recede or cool, its world shrinks. While we can't map its exact routes, the fossil record suggests something similar to today's major marine highways. Passages where whales now migrate between breeding and feeding grounds were likely once rich biological corridors teeming with prey. In that environment, this shark could have been a constant and unwelcome companion, following pods of cetaceans, taking advantage of the same routes, the same submarine valleys, the same shelf edges. What's interesting is that, despite its dominance, its trail is fragmentary. We don't have graveyards of complete skeletons. We don't have a star fossil that shows us its entire silhouette. The reason is simple and brutal. Sharks are made of cartilage, not bone. Cartilage disintegrates, rots, and is lost. What remains are the harder parts: teeth, fragments of jaws, mineralized vertebrae. The rest of the animal disappears into the depths of the sea, just as it disappeared from history. This combination of abundance and emptiness is one of the most fascinating paradoxes of studying it. Its teeth are everywhere: museums, private collections, quarries, marine fossil fields. We know it was common. We know it was distributed across the entire planet. But we don't know precisely what its body looked like, what its proportions were, what its dorsal fin looked like silhouetted against the surface. These are enormous gaps in our knowledge for such an important predator. And yet, a single tooth is enough to sense its presence. The size, the triangular shape, the serrated edges, everything seems to say the same thing. This animal was designed to cut through flesh and bone on a massive scale. Each fossil is a tiny clue about a gigantic organism. When a shark dies, almost its entire body disappears. The cartilage disintegrates. The soft tissues become food for other animals. The only parts that withstand the test of time are the most mineralized. And in sharks, that means above all the teeth. That's why the fossil record of this species is basically a shower of giant teeth scattered across half the planet. A shark doesn't have just one row of teeth. It has several, arranged like a conveyor belt. When a tooth falls out, another moves forward and takes its place. Throughout its life, it can produce thousands. Each one is a small capsule of information: size, shape, thickness, wear. Together, this data allows us to patiently reconstruct the dimensions of the animal that carried them in its mouth. If we know the relationship between tooth size and body length in modern sharks, we can extrapolate it. That's what the first researchers did. They took large sharks like the great white, measured their teeth and their total length, plotted a mathematical relationship, and then applied that relationship to the fossil teeth of this predator. The result was astonishing. The figures skyrocketed far beyond any living shark. Over time, the method was refined. A single tooth isn't enough. The tooth's position in the jaw changes its size. A front tooth isn't the same size as a side tooth, so paleontologists began identifying which tooth corresponded to which part of the mouth. They compared the curvature, the angle, the width of the root. Only then did they use these well-placed teeth to estimate the total length. Even then, the margin of error remained large. Then, comparative anatomy came into play. For years, this shark was thought to be a close relative of the great white shark. That assumption influenced almost everything: the reconstructions of its body, the shape of its head, the robustness of its torso. Later, new analyses of teeth and fossil lineages suggested that it actually belonged to another branch of extinct sharks. This forced a revision of the model's proportions. The monster was still gigantic, but its silhouette changed in the scientific drawings. In parallel, a few fossil vertebrae provided additional clues. They are rare, but when they appear, they are enormous, with growth rings that can be counted like those of a tree. These rings give an idea of the individual's age and the rate at which it grew. From there, growth curves can be constructed. How many years it took to reach certain sizes, how much energy it required, what kind of life strategy it followed. All of this, again, from a handful of rings in a piece of mineralized cartilage. Another key field is the study of bite marks. Semicircular impressions, embedded teeth, and deep grooves are observed on fossil whale bones. By measuring the distance between these marks, the size of the jaw can be reconstructed. From the bite arc, the width of the mouth can be inferred. And from the mouth, the head, and by extension, the entire body, can be modeled. It's not unlike reconstructing the size of a wolf from the bite mark it left on a deer bone. Only here, everything occurs on a planetary scale. With this data in hand, biomechanics comes into play. Three-dimensional models of jaws are created based on modern sharks, scaled to the inferred size of this predator. Forces are applied, mouth closure is simulated, and stresses in the cartilage are calculated. And from there come the famous bite force estimates, figures that far exceed those of any known predator, capable of fracturing whale bones and opening large wounds with a single attack. But every step has its drawbacks. If the modern shark we use as a basis isn't the right relative, the model becomes distorted. If we overestimate the body's robustness, we inflate the mass and strength. If this fossil shark's jaw had a different architecture, some simulations might be wrong. That's why there are constant revisions, studies that reduce the traditional maximum sizes. works that propose somewhat more slender or more compact bodies, hypotheses that change details of the head, the dorsal fin, or the tail. Even the famous reconstructed jaws we see in museums are, in part, interpretations. Many are assembled with teeth from different individuals. Gaps are filled with replicas. The curvature is adjusted so that the arch looks natural on a human scale. The result is visually striking, but it's not an exact mold of a real mouth. It's a better approximation, built with what we have and with the need to show something tangible to visitors. Science is aware of these limitations. Therefore, in recent years, some groups have preferred to use more conservative statistical models. They do not extrapolate beyond what the data allows. They limit the range of possible lengths. They calculate several versions of the same animal, a minimum, an average, and a maximum. Instead of talking about the size of the predator, they talk about a probable range of sizes, conditioned by the method used. And yet, the overall picture remains. Any of these scenarios depicts a gigantic shark, much larger than those of today, with enormous jaws and teeth designed to slice through large chunks of flesh. The differences between models change the fine print, not the core message. The creature still occupies the upper end of the spectrum of marine predators. This entire process, from the first tooth collected on a beach to the most sophisticated computer model, reveals something important. Reconstructing an extinct animal is not an act of unbridled imagination. It is an exercise in discipline. It begins with the little that is known for certain. It compares with living organisms. It applies physical laws that remain valid, whether millions of years have passed or not. And it honestly acknowledges where the data ends and where speculation begins. What we're really missing is no longer just drawing its shape. It's understanding how that body behaved in the sea, how far it swam, how it hunted, what strategies it used to capture prey as large as a whale. A body weighing tens of tons needs a constant flow of calories. That's not achieved by hunting small fish. Everything points to it having focused a good part of its diet on marine mammals. Young whales, medium-sized adults, dolphins, primitive seals, and other large marine vertebrates. The fossil bones of these animals show bite marks that fit their teeth, semicircular arcs, deep cuts, chunks torn off with a single bite. These marks also tell a story of strategy. Many appear in the tail region, on the flippers, or near the caudal peduncle. Striking there makes sense. An animal that loses the ability to propel itself is doomed. There's no need to kill it immediately. It's enough to immobilize it. The predator can then retreat a few meters, wait for the victim to weaken, and finish it off with further bites. Some fossil whales show repeated attack patterns, as if the same type of ambush had been used over and over again for millions of years. The typical hunting grounds would be the continental shelves and their edges, areas where depth changes rapidly, where nutrient-rich waters mix, and where prey congregate. There, cetacean migratory routes, schools of fish, and groups of sharks could intersect. An adult of this species likely patrolled these edges like a hunter who knew every nook and cranny of its territory, taking advantage of changes in light, currents, and the distraction of prey groups. Its senses had to be up to the task. All large sharks share a refined sensory arsenal, an extremely sensitive sense of smell to detect blood at long distances. The ability to perceive pressure changes with the lateral line, and electrical receptors in the snout capable of detecting the weak electrical fields generated by the muscles of other animals. Scaling all of that up to a gigantic body means an animal capable of locating an opportunity from miles away, tracking it, and attacking at the moment of greatest advantage. It wouldn't always be a long chase. Such a large body isn't designed for prolonged runs at top speed. It most likely combined relatively efficient cruising movements with short but devastating bursts of acceleration. Ambushes from below, using the water column for cover. Attacks from the side, using the mass of its own body as a battering ram. Measured blows that maximized damage and minimized energy expenditure. It also likely didn't shy away from scavenging. A whale carcass provides an enormous amount of energy. If this shark found a body floating or slowly sinking, it had no reason to pass it up. Fossil teeth embedded in bones suggest it wasn't always the first attacker. Sometimes it would arrive later, displacing other smaller predators or sharks to get the best part. A superpredator doesn't just hunt, It also dominates opportunities that others can't defend. Its story isn't limited to hunting. It also had to reproduce. Most sharks in its group are viviparous. The pups develop inside the mother and are born fully formed, ready to swim. In some present-day species, the embryos feed on unfertilized eggs or even other embryos. This strategy produces few pups, but very large and resilient ones. If this shark followed a similar pattern, each birth was a huge investment of resources in a few very robust pups. Evidence of this comes in another form, the so-called nursery sites, fossil zones where small teeth from juvenile sharks are abundant, in warm, relatively shallow coastal environments. There, the pups would have had less risk of encountering other giant predators and more access to smaller prey. This is similar to present-day bays where young sharks grow up protected among mangroves, estuaries, and murky waters, a natural nursery in which to spend their first years of life. If we look at fossilized vertebrae, we can count growth rings. Each ring indicates a stage of development, just like trees. This suggests rapid growth during the early years and relatively late sexual maturity, perhaps at 10 or 15 years of age. From then on, growth would slow, but the animal would continue to gain mass for decades. This is a typical pattern for large, long-lived predators. Few offspring, indirect care through the choice of safe habitats, and a strong dependence on ecosystem stability. The big question remains, did it live alone or in groups? Here, the fossil record is almost silent. We don't have snapshots of several individuals attacking together, but we don't have them for many other predators either, and we know that some cooperate. The most prudent approach is to imagine it as a primarily solitary animal, like many large sharks today, with possible temporary aggregations. Gatherings around abundant food sources, coinciding migrations, or shared breeding grounds. At a whale-feeding frenzy, for example, it's possible that several individuals might have crossed paths. The question is whether that was genuine cooperation or simply coincidence. Several predators seizing the same opportunity, but each on its own, with hierarchies determined by size. The largest would take the best portions. The smaller ones would wait their turn or settle for the scraps. It's a dynamic we see in the ocean today, and it fits well with an ecosystem dominated by a few giants and many smaller competitors. For millions of years, everything seemed to work in their favor. The climate was warm, prey was plentiful, whale migration routes offered a predictable food supply, and yet a moment came when that stability was shattered. The giant vanished from the fossil record, without a farewell, without a clear catastrophe, only an ever-lengthening silence in the rocks. To understand this, we must look at the planet, not the shark. Toward the end of the Miocene and the beginning of the Pliocene, the Earth began to cool. The polar ice caps grew. Temperature differences between the equator and the poles intensified. Sea levels fell. Many shallow platforms, those underwater tabletops where life was concentrated, were reduced or transformed. The oceans changed their character. They ceased to be the warm, stable paradise in which this predator had thrived. At the same time, ocean currents were reorganized. One of the most significant events was the gradual closure of the passage connecting the Pacific and Atlantic Oceans in the region now occupied by the Isthmus of Panama. This land bridge not only separated two seas, it altered the transport of heat and salinity on a global scale. It changed rainfall patterns. It altered the productivity of different marine basins. What was once a warm, nutrient-rich highway became, in some cases, a more fragmented and uneven system. The prey changed too. Cetacean radiation continued, but under new rules. Many whales began exploiting cooler, more productive waters, farther from the tropical belts where this shark felt most at home. Migratory routes lengthened or shifted. Some species disappeared, replaced by lineages better adapted to the new temperature gradients. For a predator specializing in large marine mammals of temperate and warm waters, this was a serious problem. Added to this was competition. It wasn't alone at the top. In the same seas lived large predatory sperm whales, capable of hunting whales and other large marine vertebrates. Later in the Pliocene, the ancestors of modern killer whales and other large dolphins appeared, employing cooperative hunting strategies. While this shark relied on brute force and ambush, these mammals could utilize social intelligence, acoustic communication, and coordinated tactics. In a cooling world, marine mammals held a key biological advantage. They are endothermic. They generate their own heat. They can maintain a relatively constant body temperature even in cold waters, provided they have enough food. A large warm water shark is much more dependent on the environment. If the waters in which its young grow cool below a certain threshold, juvenile survival suffers. If prey migration routes shift to less favorable latitudes, its energy margins narrow. The combination of factors becomes clear: fewer warm surface seas, changes in the distribution of medium-sized whales, perhaps its central resource, more competition with other large predators that tolerate colder waters better. A life strategy based on few large offspring and slow growth, highly sensitive to any increase in juvenile mortality or reduction in reproductive success. It doesn't take a single disaster. A series of small, accumulated pressures can be enough to push a species to the brink. The fossil record tells the story indirectly. As we move toward the late Pliocene, this shark's teeth become less frequent in the sediments. There are debates about the exact date of its disappearance, but most data place the extinction between 4 and 2.6 million years ago. In the younger strata, where remains of other sharks and marine mammals do appear, we no longer find its characteristic teeth. It's as if someone erased its presence from the ecosystem. Nor can we rule out internal factors within the population itself. If the species already had little genetic diversity, if its distribution was more fragmented than fossils suggest, if certain key subpopulations disappeared before others, the decline could have accelerated. But those details are, for now, invisible. We don't have DNA. We don't have fossil record continuous enough to trace its history generation by generation. We see isolated points in time, not a complete picture. From an ecological perspective, its disappearance created gaps. Other predators filled its niche, at least in part. Orcas and other predatory dolphins expanded their range. Great white sharks consolidated their role as apex predators in many seas. The structure of food chains was reconfigured, and while this animal disappeared from the ocean millions of years ago in our imagination, it never left. For decades, its true size was debated. Figures circulated without much filtering. People talked about 25 meters as if it were commonplace, about colossal weights, about mouths capable of swallowing small boats. More recent studies have proposed more moderate estimates. They are still enormous, but not limitless. It's not that they lied before, but rather that they worked with simpler methods and less data. The revision doesn't make the animal any less impressive. It makes it more believable. The same is true of its lineage. For a long time, it was assumed to be basically a giant version of the great white shark. That idea crystallized in illustrations, models, and special effects. Then, analyses of its lineage showed that it belonged to another extinct group. The resemblance to the great white shark would be more a case of convergent evolution than a direct relationship. Even so, the image of the giant white shark remains dominant in film and television. It's simple, recognizable, and easy to use in a story, even if it's not entirely accurate. Another source of confusion is the dates. The extinction is generally placed between 4 and 2.6 million years ago, but this broad range has led to misunderstandings. Some have interpreted 2.6 million years as yesterday in geological terms. Hence phrases like, "it could have survived somewhere." They sound reasonable, but they ignore something essential. The fossil record of other sharks, whales, and marine vertebrates does continue afterward. Their teeth keep turning up, theirs don't. If a significant population had persisted, we would expect to find remains in younger layers. That's not the case. Even so, every now and then a supposedly recent tooth appears in eye-catching headlines. Most are resolved in much less spectacular ways. Errors in sediment dating, material transported from older layers, or isolated pieces found out of stratigraphic context. Without a clear layer and well-dated accompanying fossils, a single tooth isn't enough to shift millions of years in the timeline. Then there are the sighting reports. Enormous shadows beneath ships, indistinct silhouettes on sonar, blurry photographs of distant fins. The sea is a breeding ground for illusions. Scale is lost. Distances are deceiving. A large shark, a whale, or even a group of animals can be mistaken for something much larger. Moreover, no sighting has been accompanied by solid evidence. Remains, clear video, consistent markings. In an ocean as exploited and monitored as today's, the idea of a stable population of giants without any conclusive evidence clashes with everything we know about biology and industrial fishing. There's also a hard biological point. This shark lived in relatively warm and productive waters, hunting marine mammals. It wasn't a specialist of the abyssal trenches. The extreme depths are cold, dark, and poor in large live prey. Most life there is sustained by the rain of organic matter that falls from the surface. It's not the ideal environment for a predator weighing tens of tons that needs to actively hunt large animals on a regular basis. Maintaining its metabolism, reproduction, and population in those environments would be nearly impossible. Why then does the idea that it might still be down there persist so strongly? In part, because of a potent mix of emotions. We are fascinated by giants. We are drawn to the possibility that the world still harbors colossal creatures, and we struggle to accept endings. The ocean, with its vastness and darkness, seems the perfect refuge for anything we want to keep alive in our imaginations. An extinct monster is a closed story. A possible monster is an open mystery. The media has exploited this tension. There have been programs presented as documentaries but which were actually disguised fictions. Recreations with actors, fabricated testimonies, computer-generated images presented as real recordings. The viewer was offered the experience of a discovery without it being made clear that it was an entertainment product. The result was confusion. For many, the line between science and spectacle became blurred. The scientific community reacted. Marine biologists, paleontologists, and science communicators came forward to explain why these productions did not represent the research consensus. They reiterated the basics: a complete absence of recent remains, incompatibility with what we know about the current ecosystem, and a lack of reproducible evidence. But a retraction always has less impact than the initial promise. A headline that says, "Perhaps it's still alive," is more appealing than an article that explains why it almost certainly isn't. Herein lies the true crux of the matter. It's not that science hasn't been able to solve the animal's mystery. We know a great deal about its approximate size, its era, its diet, and its role in the ecosystem. What remains unclear are the finer details: its exact maximum length, the precise shape of its body, its patterns of social behavior, the specific scene of its disappearance. These margins of uncertainty are not a flaw in the methodology. They are part of its honesty. Science has no problem saying, "We don't know yet," or "We can only estimate it within this range." This way of thinking clashes with the human desire for definitive answers. Some fill it with exaggeration, others with denial. Between these two extremes lies a fertile space, that of informed wonder. Accepting that an animal can be at the same time well known in its general features and mysterious in its details. Perhaps therein lies its most enduring appeal. It was not only one of the greatest predators to have ever swum in the ocean, it is also a mirror to our own limitations. It reminds us that even with technology, models, and decades of work, there will be creatures from the past that we will never fully understand, and that this is not a defeat. It is a permanent invitation to keep asking questions, to keep investigating, and to live with the idea that beneath the surface of time there will always be shadowy areas,